electric wheelchairs are widely used as they provide disabled users the ability to move around independently. However, depending on the severity of their disabilities, some users may not be able to control the electric wheelchairs safely and efficiently. This can lead to unfortunate accidents when the user loses control over the wheelchair or due to poor navigation. I'm Yin Yakbui, and my supervisor, Dr. Ali Goktugan, aimed to address the problem through my thesis, development of a teleoperated smart electric wheelchair with multimodal human-machine interface and semi-autonomous navigation. A smart electric wheelchair has been developed to provide speech control,
Turn left 90 degrees.
Wheelchair will turn left.
Go forward.
Wheelchair will move forward.
Turn right.
Wheelchair will turn right.
Go forward.
Wheelchair will move forward.
Speech control allows the user to easily control the wheelchair indoors or along a path. In addition to speech control, the user can also control the smart electric wheelchair using teleoperation control over a browser. Finally, the smart electric wheelchair can semi-autonomously navigate following defined waypoints. The waypoints are defined using a web application that has been developed specifically for the smart electric wheelchair. Within this web application, the user can add, remove waypoints or change the settings. Then the mission can be saved and loaded locally or online at the server. Finally, the users can monitor a live mission. To efficiently control the wheelchair, the electric wheelchair is modeled with a differential drive kinematic with the constraints: no lateral slip motion, no skidding, and no slipping motion. The differential drive kinematic allows the travel direction of the wheelchair to be determined by the angular velocity of each of the two individual wheels. In 2, the turning speed of two wheels is defined by the joystick. The joystick is controlled by a 3D printed joystick controller using two digital servos, each controlling an axis of the joystick movement. The joystick movement can be defined along two axes, where the distance along each axis is measured as A and B. Using A and B, a ratio can be obtained to determine the angular velocity of each of the two wheels. This means that from the joystick position, the change of the wheelchair position in the wheel frame can be determined. To integrate the smart electric wheelchair system into an electric wheelchair, it is equipped with a global navigation satellite system antenna, a microphone, speaker, joystick controller, ultrasonic sensors, and finally an electronics enclosure. Inside the electronic enclosure, there is a Raspberry Pi 4 Model B that acts as the brain of the system, continuously communicate with the server and monitoring your GNSS sensor, IMU, and the Arduino. The Arduino is responsible for interfacing with the voltage sensor to monitor the wheelchair battery voltage and monitoring the ultrasonic sensors for nearby obstacles. Finally, the Arduino listens for the command from the Raspberry Pi to control the servos on the joystick controller. To control the electric wheelchair by speech commands, Google Assistant is used as an online speech interface through Dialogflow that communicates with the server through WebSocket after each command is recognized. To recognize speech, when internet connection is unavailable, the offline speech recognition toolkit Raspberry is used within a Docker that communicates with the wheelchair client through a local WebSocket. For compatibility throughout a wide range of devices with internet access, React.js is utilized as a front-end framework for the web application, and the server is implemented in Node.js with Express framework. The Wheelchair client is also implemented in Node.js with the use of Journey 5 robotic framework. To teleoperate the Smart Electric Wheelchair or to monitor a live mission, the live teleoperation interface of the Smart Electric Wheelchair web application is used. On this interface, the user can also use the visual joystick as they would control the wheelchair joystick. The user can also see if there is any obstacle nearby using the radar plot, or the user can control an ongoing mission by stopping, pausing, or starting over. There is also a settings option to change the PID coefficients and a live plot view of the data for all of the sensors equipped on the wheelchair. To semi-autonomously navigate between waypoints, the wheelchair needs to know where it currently is, its relative position to the waypoints, and how close it is to the waypoints. To achieve this, global satellite navigation system is utilized, where a position can be represented as a pair of latitude and longitude values. With real-time kinematic, this method is ideal for outdoor navigation with centimeters accuracy. To calculate the distance between the current position A to the waypoint B, Havelsan formula is used to provide the geodesic distance estimate, which uses the spherical model of the Earth. Finally, trigonometry between the position A and position B is used to calculate the bearing. In PID waypoint following, the Smart Electric Wheelchair will navigate from waypoint to waypoint by maintaining the heading in a straight path using a heading PID controller. When a waypoint is reached, heading angle to the next waypoint is calculated, and the Smart Electric Wheelchair turns in that direction and proceeds until the last waypoint is reached. Instead of navigation by going from waypoint to waypoint, pull pursuit method is implemented to follow the path defined by the waypoints. Pull pursuit method is an algorithm that computes a curvature from the current position to a goal position at L distance. This can be illustrated by the two circles. A circle is centered at the wheelchair's position, phi wheelchair and lambda wheelchair, with the radius L, which is the look-ahead distance. The second circle with radius R track, which is the radius of the curvature, intersects with the center of the first circle and the path at the look-ahead points, phi look-ahead and lambda look-ahead. The goal is to find a curvature for the wheelchair to follow by the radius R track within the wheelchair's position at the look-ahead points. When the wheelchair is close to the path, a fixed look-ahead distance is sufficient. However, when the wheelchair is distant from the path, this system can behave abruptly. Therefore, an adaptive look-ahead distance L-adapt is calculated from the sum of the look-ahead distance and normal distance from the line segments. To demonstrate the obstacle detection functionality of SU, missions are defined with obstacles obstructing the path as well as persons stepping into the path. The wheelchair then stops in front of the obstacle if the distance is less than 1.5 meters. If the path is clear, the wheelchair will continue with the path. To experiment pull pursuit, different look-ahead values are tested. As shown here is the result of pull pursuit with 0.6 look-ahead distance. This short look-ahead caused the wheelchair to oscillate along a path with aggressive turns at the corners. For a longer look-ahead distance of 1.2 meters, the wheelchair sticks closely to the path with less aggressive turns. However, a fixed long look-ahead distance can also cause large lateral error from the path. As shown here are the paths by a fixed 1 meter look ahead distance and an adaptive 0.85 meters look ahead distance. The adaptive shorter look ahead distance allows the wheelchair to stick closer to the path with less lateral error. PAD waypoint following is efficient at following short waypoint segments and straight path. However, for segments with longer distances and more turns, the algorithm produces significant deviation from the path. The performance of PAD waypoint following and pull pursuit are experimented on the same path. As shown in the figure, the PAD waypoint following algorithm allows the wheelchair to stay close to the path for shorter segments. However, for longer segments, there is an increasing lateral error from the path compared to pull pursuit, which stays closely to the path. This is due to the PAD waypoint following algorithm tracks the waypoint instead of the path as pull pursuit does. Finally, the performance between Google Assistant and Raspberry has been experimented by repeating each of the 9 movement commands by 20 times. It has been found that Raspberry is more robust at detecting intent of shorter commands, and Google Assistant is more flexible with more complex commands with different options. As Raspberry is implemented offline and locally with the client software, it also provides slow speech processing time. In conclusion, a smart electric wheelchair has been developed where an electric wheelchair has been integrated with speech control, teleoperation control, and semi-autonomous waypoint navigation. And the result has been demonstrated by the experiments. I'm grateful that I had the opportunity to work on this project. I've learned about semi-autonomous waypoint navigation theory and its implementation. I've also learned about how to integrate mechanical, electronic, and software components onto electric wheelchair systems. I learned how to develop real-time application to interact with robotic client software and how to implement efficient data communications. I have also obtained an excellent wheelchair driving skill. In the future, the system can be improved by investigating the combination of pull pursuit and PAD waypoint following. Autonomous obstacle avoidance and traversable path detection would also be beneficial in ensuring the user's safety. And that has been my video on semi-autonomous smart electric wheelchair. I would like to thank my family and friends for their unconditional and continuous support. I would also like to express my deepest gratitude towards my supervisor, Dr. Ali Goktogan, who has been providing me endless support and help throughout this journey, providing me the chance to recognize my true potential and flaws. Thank you so much for watching. Take care.